Welcome to the ChemDoctor, and this video is in response to a request I've had on my website to produce more videos that deal with limiting reactants and theoretical yields. Now, this is a fairly sophisticated problem, and I highly recommend that you see the more basic videos before you attempt to this one. We are going to deal with several different concept areas here. We have a limiting reactant problem that has to be solved. We're going to calculate a percent yield for this reaction, and we're also going to calculate mass of the remaining reactant. And so let me go ahead and read the question. We've got 28.5 grams of KCl that's been combined with 25.7 grams of lead 2 ion, and they give us the actual yield of, I see that I didn't write this the best, so this is the actual yield of lead 2 chloride is 29.4 grams, so they've given us an actual. We're going to calculate the theoretical yield of the lead chloride and the mass of the remaining reactant, and we're going to calculate the percent yield for the reaction. All right, so we have a lot of work to do. Now, to deal with a problem like this, what you're going to want to accomplish first is to calculate the limiting reactant, because before we can calculate the percent yield, for example, we're going to have to know the theoretical yield. So what I'm going to do is rewrite my chemical equation here that we've been given. So we're going to have lead 2 ion that's reacting with 2 moles of KCl, and it will produce lead chloride or lead 2 chloride and 2 moles of potassium ion. All right, and this is a net ionic equation, which is the reason why you see ions in it. The spectator ions have been canceled out. If you want to learn about that, you'll find other videos that deal with writing net ionic equations at my website, www.chemdoctor.org. In the meantime, let's get down the road with this. So let's go ahead and write our information in. So we're going to have 25.7 grams of the lead ion. We're going to have 28.5 grams of the KCl. The designated product, all right, we're being asked to find the theoretical yield of lead chloride. So, and they give us the actual yield here. So I'll go ahead and use a question mark here to indicate that we're looking for the theoretical yield of the lead chloride. Now, this is a classic limiting reactant problem, so we're going to go ahead and pull down the information that we've been given. Don't forget the units, and don't leave off your labels. You need to know who it is you're dealing with here. Otherwise, in a problem this extensive, you're going to get lost. All right, here's the KCl. Now, we're in mass. Remember that we need to be in the same units as the coefficients of the balanced equation, and the coefficients are in units of moles. All right, so we need to be in the same exact units. There's a 1 here, and then there's a 2 for this coefficient. So the coefficients are always in units of moles. So our initial calculation here is going to be to take our mass and convert to moles. Now, when you look up on the periodic table, you'll see that the molar mass of the lead, I'm going to change colors here, is 207.2 grams. I'll go ahead and put that in here. If you need to pause the video to grab yourself a periodic table, go ahead and do that, so that you can keep up with the basic calculations I'm doing. When you calculate the KCl, the K is about 40 grams per mole. The chlorine comes in at 35.45. So the molar mass of the KCl is going to be 74.55 grams per mole. And this is my KCl. And this is my lead. All right, and you can see that the mass of the lead cancels with mass of lead, and the mass of the KCl cancels out with grams of KCl. All right, so we've successfully solved for the moles of both of these. I'm going to go ahead and write my label before I deal with my numbers. So we have moles of lead there, and down here we're going to have moles of KCl. So remember the game here. We're calculating the theoretical yield of lead chloride using both reactants as if the other reactant is in excess. When we get the moles of the lead chloride calculated using both reactants, then we're going to compare those two numbers, determine which of the two values is smaller, and recognize that that value had to come from the limiting reactant. All right, so let's see what we got here. All right, so the moles of the lead is 0.124. The moles of my KCl is 0.382. All right, now we're going to go ahead and solve using a ratio from the balanced equation to calculate for the moles of the lead chloride. So moles of the lead chloride, theoretical yield, which is the goal of this, right? Because we need to compare and see which of the two values is the smaller amount. Right? And this one's going to be moles lead chloride as well. Now, for the top stream of calculation, all right, we're going to have 1 PbCl2 in the top, and for the bottom, we're solving for the same thing, so it's going to be 1 PbCl2 here. In the top stream, we want to cancel the lead. So the lead has a coefficient also of 1. For the bottom one, we're in the KCl, so it's going to be 2 KCl's here. The coefficients, once again, come from the coefficients of the balanced equation. So the top stream is going to yield 0.124 moles of the lead chloride, and the bottom one is going to yield 0.191 moles of lead chloride. So now, comparing my two numbers, you can clearly see that the top stream is producing less lead chloride than the bottom one. So I'm going to come over here and I'm going to circle this. This is my LR right here. All right, and my excess is the KCl. All right, now we're one step away from having theoretical yield in mass, so I'm going to be multiplying the lead chloride, the lesser amount, by the molar mass, which should be 278.1 grams per mole of lead chloride. So my molesies cancels with the molesies, and I'll just put it up here. This is going to equal a total of 34.5 grams PbCl2. Remember, as we go through this, the smart thing to do is to be pausing the video and making the calculations yourself, so that you process everything the same as I am, and then you may actually find a mistake I make, and if that happens, please comment the video so I can go in and fix the mistake. All right, so this is our theoretical yield. I'm going to label it Theo yield in mass of the lead chloride. Now, we can go ahead right now at this juncture and calculate our percent yield. And remember, maybe I'll put it down here out of the way to remind the viewer, our percent yield is going to equal the actual yield, I'll abbreviate it ACT, over the theoretical yield times 100. So the percent yield for this reaction is going to equal, all right, here's our actual right here. So 29.4 divided by 34.5 times 100. So my percent yield for the reaction is going to be 85.2%. All right, so that's the percent yield for the reaction. The theoretical yield, once again, to remind the viewer, this is the maximum mass of lead chloride that could be produced by this reaction if all of the limiting reactant reacted and the reaction was 100% efficient and there were no losses. No chemical reaction is 100% efficient. So in this example, the actual yield was 29.4 and the percent yield was 85.2%. So this reaction you could think of, in a way of thinking, was about 85% efficient. Now, for the next part of this, most of the time in these reactions you're going to be asked to find the mass of the remaining reactant. So what we have to do first is find the mass of how much of the reactant in excess reacted with the limiting reactant. Remember, the only way you can do this is to use the limiting reactant itself to find the mass of the other reactant that reacted with it. So I'm going to pull down the moles of the limiting reactant. We have 0.124 moles of lead ion that is the limiting reactant. We're going to find the amount of the KCl that reacted with this. So we're going to need to put the KCl in the numerator. The 2 here came from the coefficient of the balanced equation. All right, and in the denominator, we're going to need the coefficient for the lead ion, which is 1, like this. So the moles of KCl that were used up in the reaction are going to be 2 times the 0.124, so it's going to be 0.248 moles of KCl, and this was used in the reaction, so I'm actually going to put that in words so I don't lose sight of what it is I'm solving for. Used up in reaction. Right, I'm going to take this to mass because I was given mass of the KCl to start with. All right, I'm going to take this to mass. I'm going to multiply. Whoops. So I'm going to multiply by the molar mass of the KCl, which is 74.55 grams per mole. All right, and you can see that the moles of KCl is canceling moles of KCl, and what I get for my mass used in the reaction is 18.5 grams of KCl used up. Okay, now to find the mass remaining, we're going to pull down my excess. So I've got 28.5 grams KCl excess. I'm going to subtract from that the amount we used. All right, and make sure to use words to indicate what I've got so you can clearly see in front of you what it is we've accomplished. All right, and what it is remaining is going to be about, there's approximately 10 grams of KCl that remains or was left over after the reaction. All right? Okay, so with that, I'd like to close the video. I want to thank the viewer for taking the time to watch. I hope it helped you with this concept area, and you can find more videos at www.chemdoctor.org. Thanks again for watching.